So we'll continue with our FBD KD exercise here. We'll look at a 15-foot beam with some weight on it. You can go ahead and read that. As it approaches the ground, brakes are applied. So there is a deceleration. Let's go ahead and draw the FBD KD. If you want to pause this, go ahead. So over on my FBD side, I have two tensions separated by 12 feet. I've got also present at 7.5 feet, I've got my 500 pounds. So those are everything that's on my FBD side. On the KD side, I'm going to go ahead and put everything right at the center of gravity. I've got mass times AY, and I've also got I bar alpha. And so if we go ahead and look at our number of unknowns right now, we've got 1, 2, 3, 4. So again, we're going to end up needing some kinematics. So if we go ahead and take a look at some of this acceleration equation, it talks about the acceleration or the deceleration of cable A and cable B. So what I'm going to do right down here is draw an acceleration diagram. And again, this is going to kind of guide us through. So over on the left side, I would have point A, which would be 20 feet per second squared. Over at point B, which again would be 12 feet away, I would have 2 feet per second squared. So again, I could relate those two through the relative acceleration equation is equal to, alpha of AB cross with RA with respect to B, and plus omega cross RA with respect to B. And again, this would be right after the brakes are applied. So I would have that omega equals 0 right there. So that term would go to 0. And so I could solve my relative acceleration equation. I could solve for alpha from that equation. That would be good. And then I could go ahead and relate the acceleration at the center of gravity to either A or B. Acceleration of A plus alpha of AB cross RG with respect to A. And so I'd be able to solve for AY. So those would be my kinematics. Got a rectangular plate with mass. I'm going to go ahead and draw the FBD KD here. Again, this is going to be from a top view. So from a coordinate point of view, just to orient you, that would be X, Z, and there would be my rotation. So again, we've got 4 tensions that are applied, but we can't see them. From the top view, what we can see is load P equal to 6 newtons right there. And then over here, we would have mass times acceleration in the Z direction. And I'd also have I bar alpha. And as we look here, we'd have unknowns of AZ and alpha. So this one actually lines up pretty nicely. And I've also got 2 equations of equilibrium. We would have a sum of the forces in the Z direction, and then also we would sum moments. So again, looking back up at the problem statement, it says immediately after the load is applied. So that would mean omega is going to equal 0. And again, what we're asked for here is to use the relative acceleration equation. Once we've used our FBD KD to solve for AZ and alpha, then we can go ahead and relate any point back to the center of gravity acceleration. So we would just be using, again, the relative acceleration equation. So we have a slender rod AB on a frictionless horizontal surface. You can go ahead and read that. Go ahead and draw the FBD KD pair. There's my slender rod. I've got X, Z, and my rotation. Up at point A to B here, we've got 36 inches. I've got applied up at A, I got 0.25 pounds. Of course, we've got now the center of gravity. We can't see the force of gravity over on the FBD because it's acting perpendicular to the view that we're looking at. And we've got here a mass of the rod times an acceleration in the x direction. And then also I bar alpha of the rod. And again, you could find that the mass of the rod was 1.75 pounds divided by G. And again, this is going to be at 18 inches. So we could find the acceleration of the center of mass. All right, we could then find the acceleration of point B by the relative acceleration equation. Again, also implied here is that this is just after the load is applied, immediately after, so that omega equals 0. So this is all going to be 0 right there. So we can go ahead and solve for the acceleration there, right? The acceleration of point B. And it says the location of the point on the bar that has 0 acceleration. And so sort of for point C, we would end up with a using an unknown r vector. And we would just use the fact that the acceleration would be equal to 0 at that point. So we'd be able to use an unknown r vector in our relative acceleration equation. So again, more FBD KDs here. And kind of read that disk B is at rest when brought into contact with disk A. Disk A has a angular velocity to it. So let's just go ahead and again draw our FBD KDs. This is going to be for disk B. So let's just kind of do this as it comes into contact. We end up with a force of friction, right, applied from A to B. So that's going to cause B to have an angular acceleration. Also over here we've got the weight of B. And we've got a reaction from the slot, call that Bx. And we'd also have down here a normal force, right, applied back onto B. So that would be our FBD KD for disk B. Put our coordinate system on there. For disk A, I'm going to do it right underneath it. It's a little bit bigger. Obviously, this is going to have an I bar A, alpha A. We've got acting opposite force of friction. I've got NB. Got reactions here, F1 and F2 from the pin. And we also have the weight of block A sitting there, of disk A. And so we end up with an FBD KD relation pair here, again for disk B, and then down here for disk A. And so we can kind of add here that alpha B and alpha A are unrelated, right, until slipping stops. And at that point, we would know the velocity at contact would be equal when they've stopped slipping. So then RB omega B would equal RA omega A. So I'll give you a minute just to read this next problem statement. Again, we're just going to draw the FBD KDs for this. So disk A and B on the left with weight D attached. We've got disk C on the right with weight E attached. So I'm going to start over on the left-hand side. With A, B, and the weight that's attached. We'll start over on the FBD side. I've got 15 pounds from the weight. I've got some reactions here from the pin. I've got 2 weights from the discs themselves. Disc A is 20 pounds and disc B is 12 pounds. All right, we've also had to cut that rope, so I've got a tension sitting right there. Over on the other side, I've got the mass of D times the acceleration of D. And up here, I've got fixed axis rotation. I've got I bar alpha. I'm going to call it alpha AB. And we've got a kinematic relationship between acceleration of D and alpha, because this is fixed axis rotation, so I would know that acceleration of D is going to be alpha times 8 inches. And again, alpha AB. So I'm going to scroll down and we're going to do now the FBD KD for C. And attached to it is the 18-pound weight. I've got reactions here from the pin, so I'm going to call that F1 and F2. I've got 12 pounds from the weight. And I've also got that tension that again had to be cut. Put a coordinate system on here. And over here I've got I bar of C times alpha C. And with the weight, I'm going to draw the arrow up. And this is the mass of E times the acceleration of E. And again, we have that same kinematic relationship with the disk at C and the edge acceleration, again in the tangential direction, so the acceleration of E is equal to alpha C times 6 inches. So if we scroll back, we've got the whole picture here. And got one more relationship that we're going to need to use here. And that's going to come if we look right back here. And I know that anything traveled on B will have to be the same as what's traveled on C. So SB equals SC, which gives me that RB theta B is going to equal RC theta C. And because RB and RC are the same, we'll have that omega C equals omega B, or that alpha B equals alpha C. And so again, down here, I've called that alpha AB is equal to alpha C. So if we kind of look at our equations and unknowns, just going to scan back down here. If we just count sum of the moments equation here, sum of the moments equation here. That would be two equations. In terms of unknowns, I'd have an unknown tension, an unknown alpha, an unknown AD, which again I know I've taken care of here. On the other side I have an alpha C and an AE, so if we count that up I'd have 5 unknowns. And again, just two equilibrium equations. So what we've derived then kinematically is one more equation, another equation, and one more equation. So we have plus 3 kinematic equations. So we'll be ready to go. We've got 5 equations, 5 unknowns. All right, our very last one now sets up a homework problem that we have. And so we've got a belt that passes between two cylinders pulled to the right by a force P. And so we end up with something that we're going to have to figure out whether or not something slips. And again, that's something that we'll get to in class in the coming days. So right now we're just going to deal with the FBD KD. This is going to be block A. I'm going to go ahead and draw a bigger block down here. Our cylinder B. Go ahead and put our coordinate system on here. And so let's see what we've got from a force point of view. On top I've got the weight, which is going to be 5 pounds. All right, I've got a horizontal force from the vertical slot. Down below I've got the belt, which again, as it gets pulled that way, it's going to apply force of friction to A. And we're going to have a normal force pushing back up on cylinder A. On B, we're going to have pushing down, right, equal and opposite of the normal force. Again, the belt, as it gets pulled through, is going to apply a force of friction to B. We're going to have the weight, which is 20 pounds, and then we're going to have some reactions to the pin right there at B. We can call that BY and BX. Over on the right-hand side, what I've got with cylinder A is just the moment of inertia of A times alpha A. Over on this side, I've got block cylinder B, which would have I bar B alpha B. And I've got one more free body diagram that we're going to need to draw. This is not a kinetic diagram, just a free body diagram. We've got that force P, which is going to be 3.6 pounds. And acting back, we've got the force of friction A and the force of friction B. And we have the normal forces NA and NA. So we've got a relationship between force of friction A, force of friction B, and the applied force. And so what we've got now is our FBD KDs. What we'll end up doing is assuming no slip. And so if we do that, then we would have that SA equals SB, which would mean that RA theta A would have to equal RB theta B, which means RA alpha A equals RB alpha B. So that'll end up being an equation that we assume, and then we end up checking to see if we've met that assumption or not. So again, that's coming up in class.